In this video, we'll be once again reviewing volumes of revolution using disks or washers. The difference between this example and the previous examples is that this one is going to use a region bounded by 3 or 4 graphs, but this time rotated around y equals -3. By rotating around y equals -3, it shifts the location of the rotation axis. In doing so, it's going to change the actual value we select for r, the radius. So to start this, we're again, as always, going to draw the image that we're looking at. For this one, we're going to look at y equals x, which is this graph right here, x equals 4, which is about here, and the x-axis, which is about here. So we have this triangle here one more time, and we're going to go ahead and rotate this around y equals -3, which is 1, 2, 3, about here. So this is the region we're trying to work with. I'm going to go ahead and highlight that. We're going to try and rotate it around this line right here. So for me to do this, I'm going to go ahead and redraw this object. I'm going to do it very carefully in such a way so I don't see very much of anything excess. The only thing I'm going to see excess is the x-axis 1, 2, 3 spaces down. Actually, that would be 0, 1, 2, 3 spaces down. This right here is our rotation axis. So I'm going to take this object and I'm going to reflect it over that axis. I'm not going to reflect it over the x-axis like I did in previous examples, but this time I have to go ahead and create a space of 1, 2, 3 units. 1, 2, 3 units. So again, when I'm going from here, 1, 2, 3, that's where it starts. From here, 1, 2, 3, that's where it starts. So now from here, in this location, I'm going to do the best of my ability to redraw that exact same triangle reflected over that dotted line. So now we see this object here, and again, it's rotating around. So we have these circular spaces inside here. You'll notice that all of this region space inside is completely empty. It's like it's been drilled out. We also have, again, this rotation here. So it'll look like, you'll notice, that we have some kind of disc-shaped object, again, cutting this vertically. But this time there's, again, a center hole that's missing. Now I'm going to make note that the rotation axis is one more time at y equals -3, and this right here is our x-axis. So the goal is to still set up the exact same type of integral. I'm still going to cut this so that I see those circular cross sections rolling around. This time, however, I just have to modify what my radius is, because my radius starts here and it's going to extend to somewhere in here. Okay, so depending on how this thing is set up, notice my outside radius is going to be way out here. That's capital R. My inside radius is always going to be this space right here. So I have a little lowercase r and a capital R, and again, the capital R, you'll notice, is changing based on this equation. Now, when I'm creating these R's, what's important to notice is that I'm not going to go to the space that I've copied it into. This isn't important. What's important is the fact that I'm going to go from this line to the region that we're integrating over. And again, we're integrating over the region, over this little triangle right here. The formulas are going to allow everything in here to be calculated appropriately, even though, again, we don't actually see much of this other stuff on this end over here being calculated. So if we recall, the way that we evaluate the integral of a disk or washer is the volume is going to be equal to, and in this case I'm going to go x equals from one number, which ends up being 0, this location right here, finding my points of intersection, and this location over here, which is simply x equals 4. So I'm going to go from 0 to 4. I'm going to integrate over the function pi r squared. Now I'm going to use capital R squared and lowercase r squared, because now it appears as though I have two different r's. If it helps, always utilize this formula as opposed to the simply integral of pi r squared d and then something. In this case, again, I know my bounds are in terms of x, so all my functions have to be in terms of x, and this will be the formula that I'm working with. Now the difficult part here is to recognize what r is in both of these equations. R in this case right here, okay, I'm going to start with the lowercase one because it's a little bit easier. No matter what x value I pick, that distance from here to here is always the same distance. Again, that distance right there is always the same distance. That radius value here will be a distance of, well, 3. Okay, now the reason why it's going to be 3 is because this y value is y equals 0, and this y value down here is y equals -3. So the way that I'm going to rewrite this is my lowercase r is equivalent to, and it's going to be, for lack of a better phrase, the upper value, or the furthest away from the rotation axis, that's 0, minus the value that the rotation axis correlates to, which is a -3. So this is the concept formula for how this r comes to be. Now again, this might be tricky or confusing to start off with, but it'll make the capital R seem more reasonable. Now our capital R, again, we're going to go out to the furthest location, which is way out here. So that function right there, which is the equation y equals x. So this equation, which again, this I'm going to call as y minus a -3. This one down here is going to be the same more or less formula, y minus a -3, where my y value is the equation of this line. So y equals, in this case, x. So it's x plus 3. And again, the concept as to why that works is because if I come up to this location right here, I'm going to go all the way down to that bar right there. So that's my capital R. But you'll notice this distance from here to here is 3. This distance from here to here is y. But that distance y is correlated specifically to this equation. So again, my radius, capital R, is this entire distance, 3 plus y. Or, again, y minus the -3 that causes this to situate itself. So now I have capital R and lowercase r, and all I simply do is plug that in to this formula over here. My volume is equal to the integral from x equals 0 to 4 of pi. Capital R is x plus 3 squared minus pi. Lowercase r is 3 squared dx. This formula right here will provide us with the volume of the object created by rotating this little triangle over y equals -3. Again, be very careful with the setup of this, and those 3's are coming from that rotation axis not being centered at the origin.